Okay. Yeah. So today we will going to actually analyze a system that is your spring mass system, where the spring is also having some weight. Okay, means generally when the mass of the spring is not means not so not, if mass of the spring is comparable with the mass of the system, okay, and if it is having some definite value, so we need to just consider the mass of the spring also. Okay, so earlier in our assumption of the analysis of an undamped free vibration of a single degree freedom system, so we did not consider the mass of the spring. Okay, but this time we are going to consider the mass of the spring as well, and we will going to see so what will be the equation of motion, or what will be the natural frequency for this system. Okay, so what is the difference in this system? That this spring mass system is having some mass in the spring. Okay, so the spring is having some mass, and it is considered, it is taken as m suffix s. Okay, ms is the mass of the spring. So here we need to determine the effect of the mass of the spring on the natural frequency. Means we are going to see the natural frequency of the spring mass system. Okay, so how we will going to analyze it? So first, so in every analysis or in every derivation, so first we need to just write down what are the things in the system. Okay, so first we will be writing all those things. So we will assume that ms is the mass of the spring. Small l we have taken, it is the length. Okay, this is called as a free length of the spring. Okay, length of the spring. And small k, this is stiffness of the spring. Okay, so its unit is Newton per meter. Yeah, one thing, so in most of the solution of the class test, okay, so you have taken means 90% of the students have taken the stiffness of the spring as Newton meter. Okay, but its unit is Newton per meter, so you should remember this one. Okay, so for this spring constant, the unit is Newton per meter. Okay, because spring force is how much? F equals to kx, so k will be what? So F by x, Newton per meter. Okay, yeah. So now let the mass m is displaced in a downward distance of x. Okay, so this displacement is x in the downward direction. So just like our previous analysis, so the velocity which will be acquired by the system, let us consider it as x dot. Okay, and acceleration is x double dot. Okay, so this velocity and acceleration is directly associated with this mass, and it is x dot and x double dot. Okay, now let us consider one small elemental length, okay, on this spring at a distance y from the free end. Okay, so this is the fixed end, sorry, not free end, this is the fixed end. So from this fixed end at a distance y, so we will be considering one small elemental length dy. Okay, so dy, this is denoted by dy, this length is dy. So out of this length L, so we have taken an elemental length of length dy. Okay, so for this elemental length dy, so what will be the velocity? Okay, so what will be the velocity? Because the mass is attached at the free end, so its velocity is how much? X dot. Okay, so as you are going upward, okay, so there will be a variation in the velocity, isn't it? The extreme end, that is the mass where it is attached, it is having a velocity x dot. Okay, and at the fixed end the velocity is how much? It is 0. Okay, here it is 0, means here it is varying. Okay, means it is changing with respect to the length. So this elemental length dy, it will be having some velocity. Okay, so how you will be finding out the velocity? So for length L, what is the velocity? X dot is the velocity. isn't it? So for length L, the velocity is x dot. Okay, for unit length, what will be the velocity? X dot by L. And for a length of y, what will be the velocity? X dot by L multiplied by y. Okay, so for this elemental length dy, okay, so where the mass of the spring is dm, this elemental mass, so the velocity will be x dot upon L multiplied by y. Okay, I think all of you have understood. So for total length of L, the velocity is how much? X dot. So for 1 unit length, the velocity will be x dot upon L. So for y length, for y distance length, the velocity will be x dot by L multiplied by y. Means this dm mass, elemental mass, is having a velocity while it is displaced. It is x dot by L into y. Okay. So if unit is meter per second, then it is meter per second. Okay, means SI unit is meter per second. Okay, so now you are you have to calculate the mass. Okay, so what will be the mass, elemental mass of this spring? The total mass of this spring is how much? It is ms. So for this elemental length, so for this elemental length, the mass will be, so dm. Okay, so dm will be how much? Ms by L, because this is the mass per unit length. For a length of L, the mass is how much? Ms. So for a length of dy, the mass will be how much? So ms by L will be unit mass. Okay, per unit length. So mass per unit length is ms by L. So multiplied by dy. So for a distance of dy, or for a length of dy, the elemental mass dm will be ms by L into dy. Okay, so what is the velocity? It is x dot upon L into y. And what is the elemental mass? So for a length of L, the mass is ms. So for unit length, the mass is ms upon L. Okay, mass per unit length. So for a length of dy, it will be ms upon L into dy. Okay, understood? Okay, now we are going to find out the kinetic energy of the spring, because the spring is displaced. Okay, actually the analysis will be done by the energy method. Okay, so what is the energy method? So the total energy of the system, it is what? It is constant. Okay, or it is conserved, constant. So if you just take the derivative of the energy, total energy, so it will be 0, isn't it? Because for constant term, the differentiation, okay, so it is 0, isn't it? So we are going to find out the total energy which are associated to this system. Okay, so to find out the kinetic energy, so we need to calculate the mass of the spring, isn't it? That is why the elemental mass, it is considered. Okay, it is taken, and the value it is given by ms upon L into dy. Now what will be the kinetic energy of the spring? So kinetic energy of the spring will be found out by integrating the kinetic energy of this elemental mass, okay, throughout the total length of the spring, means from 0 to L. So if we can integrate the elemental kinetic energy, then we will get the total kinetic energy of the spring. Understood? So the elemental mass is dm, okay, and the velocity we have found out it to be x dot upon L into y. Okay, so mass half mv square will be the kinetic energy for the spring. Okay, so for this elemental length, so we are going to find out half mv square. So integration 0 to L. So for the whole length of the spring, so you need to integrate from 0 to L. So half mv square. So half by formula, what is m? So mass of the spring, this elemental mass is what? ms upon L into dy. So this is the elemental mass of the spring. Okay, elemental spring. Then what is the velocity? X dot upon L into y. X dot upon L into y means for this elemental length or elemental mass, so this is the kinetic energy. Okay, elemental kinetic energy. So if you just integrate from 0 to L, so you will get the total kinetic energy of the spring. Okay, so after calculation, what you will get? So this is constant, so half will comes out, then ms upon l. Okay, so x dot upon l, so x dot square by l square. So variable will be y dy. Okay, y dy will be how much? Y square dy. So y cube by 3. Okay, so if you put just lower limit and upper limit and lower limit, then you will get l cube by 3. So directly I have written. Okay, so this is very easy integration. So half ms upon l for this x dot by l, so square is there, square will be there, square square, then y cube upon 3. Okay, so if you just put lower limit and upper limit, so upper limit minus lower limit, you will get l cube. Okay, so after simplification, here l cube will be cancelled out, only ms and x dot term will be there. So 1 upon 6, because this 3 is there, so 2 into 3, it is 6. So half ms into x dot square. Okay, so this is the kinetic energy of the spring, but we need to consider the kinetic energy of this mass also. Okay, so for this spring, so 1 upon 6 ms into x dot square is the kinetic energy of the spring. So in GATE exam, so directly it is asked that what is the kinetic energy of the spring. Okay, when you are analyzing a spring mass system where the spring is having a mass. Okay, so then you need to write that 1 upon 6 ms into x dot square. Okay, now what is the potential energy of the spring? So it is very easy, half kx square is the potential energy of the spring. Okay, half kx square. So for this system, the main components are spring and the mass. So for this spring, the potential energy it is written, and for this spring, the kinetic energy it is written. Okay, so kinetic energy it is found out. Okay, those two terms. Now the total energy associated with the system will be what? So half kx square. So this is the potential energy of the spring. So half mx dot square. This is the kinetic energy of the mass. Okay, so this m is dominating over this ms, isn't it? Because it is having some mass. It may be 2 kg and here it may be 10 gram. Okay, or here it may be 50 gram. Okay, so like that. So we need to just write down the kinetic energy for this main mass. Okay, primary mass also. So half mx dot square. Okay, so then kinetic energy of the spring, so 1 upon 6 ms into x dot square. So if you just rearrange all this term and after calculation and after a simplification, so you will get half kx square. So now you can add these two terms because x dot square and x dot square term it is there. Okay, so if you just calculate, so you can take half common, half m plus ms by 6. Okay, as because it is 2, here it is 3. Okay, so ms by 3 bracket close x dot square. Okay, and if you just compare this equation with our spring mass system equation, so these equations are similar. Okay, only the coefficients are different. Okay, so from this expression, so directly you can write the natural frequency, isn't it? And if you are asked to find out what is the equation of motion, then you need to find out d by dx. Okay, d by dx dt, d by dt will be equals to 0, isn't it? So total energy with respect to time, it is 0, isn't it? Because this value is constant. This value of the total energy, it is constant. So if you just differentiate it, you will get the whole equation of the motion of the system. Okay, and from that you can find out the natural frequency, and directly from this expression also, so you can find out the natural frequency of the system. So it will be how much? So k by m plus ms by 3. Okay, so its unit is radian per second. So this is the circular frequency or the frequency, natural frequency of the systems. Okay, so similarly you can find out the linear frequency also for this spring mass system, where we are considering some mass which is associated with this spring. Understood? So in this way, so you need to analyze this type of system, okay, by energy method. I think this concept is clear to all of you. If you have any doubt, you can ask me. Anyone, if you have not understood? then you can ask me. Okay, should I repeat it? Anyone please respond in the message, text message. Dixita? Okay.
Yes, sir.
Okay. So I think this concept is clear to you. Yeah. Okay. So yes, Sivanos, are you there? Sivanos?
Yes, sir.
Okay. So have you understood this topic?
Yes, sir.
Okay. Okay. So yeah. So today we will finish this undamped part of vibration, okay, by doing some problem. Okay, so I have taken some problem directly from the book, so we will discuss it here. Then we will finish this chapter, and we will move in the next class. Directly we will move to the damped vibration. So here one problem, it is from the module 1, I think. Okay, yeah. A spring mass system has natural frequency of 12 hertz. So when the spring constant is reduced by 800 Newton per meter, the frequency is changed by 50%. Okay, so this type of question, similar question, actually it was asked in the class test. Okay, so very easy problem, aptitude type problem. So determine the mass and the spring constant of the original system. Okay, so it is given that one system which is having spring mass combination, so its natural frequency is 12 hertz. So here it is given as 12 hertz, means what? So this is F. Okay, this is not Wn or omega n, this is small f. Okay, frequency. So 12 will be equals to 1 upon 2 pi under root k by m, because under root k by m is the natural frequency of the system. So f equals to, or f1 will be equals to 1 upon 2 pi under root k by m. Okay, so this is given from the first line. So when the spring constant is reduced by 800, okay, so earlier the spring constant is how much? Small k. Now it is reduced by 800. So small k minus 800, the frequency is changed by 50%. So earlier the frequency was 12. So if it is reduced by 50%, the frequency will be 6. Okay, so here k minus 800 will be there. So two equations, so two unknown. So you need to solve these two equations, and directly by dividing, okay, after division, so you will get the value of one parameter. Okay, so here it is k. So if you just come to know the value of k, so if you will put the value of k in any one of these equation, so directly you will get the value of this mass. Okay, so this type of questions will be asked. Okay, or it may be asked, and this type of questions you will get in the GATE examination also. Okay, so those questions are not that tough, though vibration it looks like it is very tough. Okay, but it directly depends on the concept. Okay, so if you just read this problem, okay, and if you do not know the vibration, so by looking at it you will guess that okay, there may be some, okay, means complexity in the question, but if you just put it, okay, in your paper, everything will be very simple. Okay, so in damped vibration also, though the problems are lengthy, or though problems look like very complex, but when you will analyze, okay, from the basics, so you will be able to solve each and every question of vibration, okay, from GATE exam. Yeah. Yes, now one problem it is there. So derive the differential equation of motion for a spring control simple pendulum. Okay, means, yeah, so this is these are the two fixed ends. So from one fixed end, the pendulum it is hanging. Okay, this is vertical pendulum, it is hanging, and from here one spring it is attached, and this displaced diagram it is not given in the question. Actually, this is the displaced position of the pendulum, though it is shown by dotted line or dotted circle. Actually the initial position is this one. Okay, vertical position of this mass m or bob m, and the spring was not stretched, okay, initially, and here in this figure the displaced diagram it is shown. Understood? So now you are asked to find out the, yeah, the spring is in its unstressed position when the pendulum rod is vertical. Yes, it is written. Actually, the basic diagram is by this line. Okay, means there will not be any dotted circle or this dotted line. So only the unstressed spring and this vertical pendulum will be there in your question. Okay. So you are asked to find out the differential equation, okay, and or the equation of motion or and the natural frequency of this system. So how you will going to solve this type of problem, okay? So though this diagram, okay, looks little bit complex, but if you just go by the basic principle, so you will come to know that this is a very simple problem, okay? Only the game is of the moments and forces, okay? So first what you will do, so you will displace the system, okay? So the system where the mass is concentrated, mass is there, so from there we will displace the system. So as because this is pendulum, so if you displace it, so there will be one angular deflection, isn't it? So you cannot displace it in linear direction, okay, because the length is L, okay? So if you just displace it linearly, so the length will increase, isn't it? So the length is restricted, constrained, okay? So for this system, okay, so if you just displace it, so the pendulum will move in this place, okay? So in this dotted circular form, so it is shown, okay, and this length is also shown in dotted line. Understood? So the weight, okay, it will act from the CG of this bob, and it is mg, okay, vertically downwards. So all the distances it is written, it is L, the length of this pendulum, and this line, okay, of the spring, it is at a distance of A from this end, okay, fixed end. Now we need to see what are the forces and moments those are acting on this system, okay? As because this is angular deflection, so we need to see the moments, okay? To see the moments, we need to see the line of action of the forces, okay? So here, as because this is displaced to the right hand side, so we can resolve this weight of this mass in two direction, one along the direction, opposite direction of this tension, okay, which will be exactly equal. That is why the bob can be placed in this position, okay? Otherwise it will just thrown away, okay, from its line, okay? That is why, as because the tension and the mg cos theta component, they are same, that is why you can show it in this position, okay? And another component will be mg sin theta. So in an inclined position, okay, so in a tangential position to this curve, so this mg sin theta line will be there, okay? So that is one force, so which due to which the bob will try to regain its original position, so in the leftward direction from this CG, so this mg sin theta, okay, so that force will act on the leftward direction, okay, means a little inclined, okay? So mg sin theta, mg cos theta will be cancelled out because of this tension, okay? So another force which will be acting because of the stretching of this spring will be acting from the right side to the left hand side, because this is stretched. So on the spring, one leftward direction force, means compressive force, will act on the spring. So what will be the value of this compressive force? So the spring constant is what? F, K. The spring constant is K. So generally, if F is the spring force, then expression of the spring force is F equals to K into X. So what is X here? Okay, so if you just resolve this triangle, so you will get that this is K into A, okay, or this is K into what? K into A theta, okay, K into A theta, because spring constant is K, A tan theta will be this distance, isn't it? So if this is the triangle, this is theta, so this side will be how much? So A tan theta, so because the theta is small, so you can write A theta, okay? So K A theta will be the force, because K into X is the force, isn't it? So A theta will be this distance, this side of this triangle, small triangle. Understood? Because theta is small, that's why you can write tan theta will be equals to theta or equivalent to theta. So A theta will be the, this distance is A, okay? So this a theta will be the displacement by which the spring is stretched, okay, or elongated. Understood? So if you just want to calculate the spring force, so it will be k into x, means k a theta will be the spring force which will be acting towards the left hand side, because this force will try to regain the original shape of the spring. Understood? So this force will act towards the left hand side. Understood? So if you just take the moment of these forces, this k a theta force and this mg sine theta, means mg theta, because theta is small, so instead of sine theta you can write mg theta. So you will get one equation. So we can write the equation as, what is Newton's second law of motion equation according to this system. So I theta double dot, because here this is angular deflection, that is why you have to write I theta double dot instead of mx double dot. Understood? So I theta double dot will be equals to the external moments. So what are the external moments? One is mg sine theta. Okay, so instead of mg sine theta, so we'll be writing mg theta, because sine theta is very small, so you can write theta instead of sine theta. So mg theta multiplied by this length, okay, multiplied by this length. So what is the length? L. So with respect to this point, okay, so you are just calculating the moment, external moment. So mg theta into L, mg theta into L. So its direction is leftward direction, means the clockwise moments are taken as negative, okay, because this theta direction is taken as positive. The displaced theta direction is from the left hand side to the right hand side, that is why it is taken as positive, okay, and this moment will be in the opposite direction of this theta direction, so that is why it is taken as negative, minus this spring force. Spring force will always act linearly, okay, and translationally, okay. So this spring force will not act in an angular way, okay. So for this spring, it will always act in translational direction, okay, in x direction or y direction or any inclined direction, okay. But you cannot resolve this spring force in any direction, okay. That is why you need to write k a theta multiplied by a. So k a square theta will be the spring force, and its direction is negative, that is why its tendency to rotate with respect to this point will be circular, okay, just like this mgl theta moment, okay. So minus k a square theta. So if you just write this equation by replacing I as ml square, okay, so ml square theta double dot plus mgl plus k square. So if you just make this common, theta common, so you will be writing this equation like this, okay, equals to 0, okay. So instead of this I, you have written ml square, mass moment of inertia of this bob with respect to this axis, okay, pivoted axis. So if you just rearrange the terms, you will get theta double dot plus mgl k square divided by ml square, so bracket close, theta equals to 0. So this equation is similar to our analysis equation, okay. So if you just compare the coefficients, so this divided by this, under root this divided by this coefficient 1, okay, so you will get the natural frequency of this system. Understood? So this is the equation of motion of the system, and this is the natural frequency of the system, okay. So directly from here, so you can write down the natural frequency. Understood? So this way you need to solve this type of problem, okay. So wherever there is a translational motion in the system, so you need to write the Newton's second law of motion as mx double dot equals to the external forces, and wherever there is a angular deflection, so you need to write the Newton's second law of equation as I theta double dot. Understood? So I theta double dot will be equals to the external moments, and the moments which you will be taking in the opposite direction of this theta, so you have to consider those moments as negative moments, just like the forces, because at the very beginning in the assumption, so I told you that all the direction of the spring mass system, so which will be taken in the downward direction, those are positive, and all the parameters which will be taken in the opposite to the displacement, those will be negative. So that similar concept it is actually applied here also in the problems, okay. So I think now you will be able to solve this type of problems, okay. So this is all about your undamped free vibration of a single degree freedom system, Okay, so if you have any doubt, then you can ask. I will upload this PDF file, okay, so in your Google Classroom. So from there also you can see this file and the video also, so I will be uploading. Okay, and time to time, okay, you have to complete all these things, otherwise see, because your exam is scheduled in December, okay, as per your academic calendar, so we have only 4 or 5 cycles, isn't it? So everything this time depends on you only. So if you just do not complete all these things on time, so just it will be a very huge, okay, means pending work, so which you won't be able to complete in time. Okay, so time to time, so you complete it. Okay, you just make the notes, as I have told you that I may ask for the notes, okay, as a kind of assignment, okay, at the end, okay, of the session. So timely you need to write all these things whatever I will cover here in our live lecture. Okay, so thank you dear students for listening. So timely you just check your Google Classroom as well as the WhatsApp group. And regarding your lab, I think all of you have started writing your lab experiments. Okay, and the calculation part is important, so you just show the calculation part, okay, in a very distinct way. Okay, don't write in small, okay, very fine, okay, small, just distinct, okay, in distinct letters, just you distinctly write it distinctly, and don't overlap, okay, over the calculation. So better you use pencils. Okay, so if some calculations you need to show, but the main calculation you will be showing through pen, okay, ball pen. Okay, and if there is some figure, so you have to draw the figure also. Okay, those figures are not that complex, only 5-6 minutes it is needed to draw the figures. Okay, so timely you just complete the lab experiments also. Okay, thank you students for listening. If you don't have any doubt, you can leave this meeting. Thank you.